My high school physics teacher was a bit of a kook. First day of class, he bit off a hunk of chalk and chomped on it while we stared at him as if he just farted or grew tentacles or something. For the next few minutes, he just crunched at us until the room became silent in a kind of horrified bafflement. He eventually said, "What? You've never had an upset stomach? This is just calcium." And then, with our full attention, he began his lecture. The experiment he described that day had to do with light. He said you could fire single photons at a detector, one that was hidden behind an obstacle with a single slit cut into it. And if you did that, the light would show up on the detector as little dots shaped in a pool, pretty much mimicking the shape of the opening that they pass through, a little line, little band. He asked us then what would happen if we cut two slits in the obstacle, one parallel to the other. So there are two slits. We were obviously still thinking about the chalk in his hand, but someone managed to offer up the obvious. Well, then you'd have two columns of dots mirroring the openings. Duh. He then showed us the results. There were two pools, as we said there'd be, but there were more, bands of them, arranged in neat sets all the way across the detector. And as we were scratching our heads, my teacher explained that light is both a particle and a wave at the same time. I remember that is the day that I learned the universe is really weird. The universe may not be as weird as we are, though. Recently, I was pursuing a pastime of mine, arguing on Facebook with conservatives. What? It's not like I'm eating glue. And yes, for the record, I do have many, many friends that are conservatives. Anyway, we were arguing about masks. I mean, seriously, how is this still an argument? And someone said something dumb about lack of consensus. And obviously, I had to correct him. And in doing so, I was all logical and linked to several studies and didn't once call him callous or a troll. And before anyone could be amazed by my restraint, one of my would-be allies immediately piled on, saying there was no point in arguing about data with conservatives because, quote, they have their truths and we have ours. And I remember arguing, wait, truth doesn't really work that way. A statement is either true or false. That's pretty much that. At no point would it matter whether or not I wanted to vote for it. Truth isn't partisan. But the thing that really annoyed me is that we weren't even talking about truth. We were talking about science. And if that distinction between truth and science sounds, well, weird, that is why I gathered you here this morning. So you can thank Facebook. Okay, at this point, I'd like you to turn to your neighbor. Yeah, it's that time in the sermon where we pay respects to my colleague, the Reverend Dr. Otis Moss, III of Trinity Church in downtown Chicago. So somewhere on the screen you're using to see my face and hear my voice, there may be little squares filled with the faces of your community. Pick one, it doesn't matter which, and then repeat after me. Neighbor, oh neighbor, science is only a tool. Thank you. Amen. So the text for today's sermon is the 1983 book, How the Laws of Physics Lie by Nancy Cartwright. If I ever write a theology or a philosophy book, my hope is that I can come up with a title half as awesome as this. You have to admire the editor that said, nah, and went with this title instead of something like Empirical Theory, the Measurement Problem, and the Functional Dissociation Between Phenomena and Covering Law. Professor Cartwright's agenda is pretty esoteric. I'm going to try and break it down. She's arguing that how we understand scientific theory and the laws of nature and how they work in scientific explanations is clumsy, inaccurate, and generally speaking, false. As in, if you can formulate a mathematical regularity that predicts something interesting about the way the universe behaves, that formulation, whether it's a model, a theory, a law, is always not true. More, that even though they are not true, science works just fine regardless. I think my professor once explained this as, quote, rather counterintuitive, which is academic ease for, this may sound completely bonkers, but bear with me a moment. So bear with me a moment. Take the weather. Pardon my layperson's phrasing, but one way of understanding how meteorologists predict the weather is that they throw darts at a board. I'm kidding. What they do is just guess. I'm sorry, this is too easy. Okay, what meteorologists actually do is that they make models. That is, meteorologists take a bunch of algorithms that reflect physical law about the behavior of gases and such, and add thermodynamics and geophysics and a whole lot more. Then they put that whole thing together and let all of that interact with each other. That's the model. To this, they might add data from reports and sensors, and maybe even tweak things with their own experiences and hunches. And when they're happy, they just let her rip, and then out pops a forecast. And sometimes that forecast is accurate. Like a theory or a law of nature, a model is an abstraction. It's a simplification, a concise way of describing some part of the world. In other words, a model resembles the world, but not exactly. Not every detail about the world is important or obviously relevant to what the model is trying to model, so it will leave stuff out. The more we leave out, the more incomplete the model, but it is easier to use or make. Of course, that may mean that some predictions will be wrong. In the case of meteorology, one outcome of a too simple model is a short forecast window. You can predict the weather this afternoon, but this weekend will be a mystery. You can, of course, make the model better. And as you do that, you might extend the predictive window, not only this weekend, but maybe the whole next week or even the next 10 days. But even with that better model, though, it's possible that 30 days out will stay completely unknown. That is, there's always a limit on how good a model can be. But by adding more data, making more assumptions explicit, by tweaking and adjusting, the idea is that there can be better predictions. And the better the predictions, the cooler the model. And there's always just some little bit more you could add. And if that sounds perfectionistic to you, it is. Because without all of those details, all of them, without all of those exceptions accounted for, without all of those things that take an abstraction to a reality, we don't necessarily have the truth. Instead, what we have is a partial story, one that never quite captures the way the world actually is. We may get near the truth, but that's it. And that's really weird. It also leads to some troubling questions. If our model, theory, or natural law isn't true, what does that mean? If the statements of science are not true, do they have any value at all? Don't panic, Cartwright argues. Remember our meteorological model. If we find ourselves having to account for every last thing before that model can make any predictions at all, if we never get to the point where we actually use the model because we are still perfecting it and reaching for the truth, what we have is paralysis, not analysis. And that's not science. In other words, in science, the truth may not set you free. Did I mention that this is counterintuitive? It does make sense to say that a perfectly good model will still miss things and not be able to do some other things. If we can predict whether it will rain next Thursday, that's pretty helpful, even if we can't predict if it will rain 6 Thursdays from now. Fact is, even with great science, there will always be exceptions to the rule, gaps in the chain of explanation, and sometimes there will be a very long list of other things that absolutely must be just so before a model, theory, or law actually works. Oops. But that's just how science works. That's just what it means when you're doing science. Approximation, a necessary lack of some accuracy or truth, has been baked into the exercise from the get-go, according to Cartwright. Yes, it sounds weird, but it works. The trick may be in managing expectations and remembering the whole point of the exercise. Fun stuff, right? Yeah. Hang in there. I want to pivot now and talk a little bit more about truth. This is interesting to me, a UU minister, because our faith tradition is all about truth. We lift up the search for truth as one of our 7 principles. Here at UUSG, our 1842 covenant calls us seekers after truth. What I want us to remember here is that when we talk about truth, it is never alone. We always pair it with the search part. As I like to say, our church is not where we come to get our questions answered, but rather to have our answers questioned. We are seekers after truth, not caretakers of truth. As theologian James Luther Adams once said, revelation is not sealed, it is ongoing, unfolding, exploding as human knowledge crashes through horizon after horizon. And that may mean that human wisdom has some catching up to do, but that's okay. As the poet Maya Angelou was said to have said, do the best you can until you know better. Then when you know better, do better. And maybe that's the best we can hope for. Maybe science should be described as the continual stretch to know more so that we can all do better. Maybe that is the point. I like to think so. Because it is through science that we get to ask really good questions, even if really good answers are elusive. That's why it's a search, a process. Science, knowledge, truth, these are paths up the mountain, not the summit itself. Sir Karl Popper, a philosopher of science in the mid-20th century, put it this way. He said that the quest for scientific knowledge was like mountain climbing. We struggle, we strive, we ascend the mountain bit by bit. Our entire path upward is wreathed in clouds and mist. Eventually, maybe if we're lucky and smart, we'll finally reach the summit. But then, as we sit there, peaceful and accomplished, a breeze stirs. And just for a moment, the mists above us part, and we're given a brief glimpse of a still higher peak and a new path upward. I suspect that many scientists around the turn of the 20th century, steeped in the deep thoughts and insights of Sir Isaac Newton, may have felt that way more than once. When a lowly patent clerk said he had found a new path to a higher peak, and with the theory of relativity showed that he attained a new height, perhaps physicists of the day were aghast, astounded, incredulous at the audacity of this young Albert Einstein. Then, having followed him to the new lofty peak and marveling at the wondrous vistas now revealed, they were perhaps aghast, astounded, and incredulous again at the audacity of Niels Bohr and others as they explored the truly bizarre world of quantum theory. each time the frontiers shifted, and each time the body of scientists that made up the academic discipline had to absorb, transmute, and then extend that new set of ideas into practice. It doesn't happen overnight, and not every revolution wins over every opposing soldier. That's one reason why scientists talk about consensus of opinion and not unanimity of understanding. I want to just sit with that a moment. Before the world changed, before the frontiers shifted and the new science won over hearts and minds, do you think any of those famous intelligent scientists would have said that what they knew, that the knowledge that they had struggled so hard to win, that all of that was false, wrong, incomplete? Would any of us say anything like that? This is, I think, the very lesson that Popper was trying to teach us all. That while science aims at truth, there's no point on the journey where a higher peak might not miraculously appear. And there is no pinnacle to knowledge, no end game, no final destination. There is no ultimate truth. Or if there is, there's no way to know we have it. There's only temporary, the seeming, the truth-like, what Popper called verisimilitude, or if you prefer, what TV personality Stephen Colbert used to call truthiness. There is, I think, this is also, I think, Professor Cartwright's point. In fact, truth isn't necessary for good science or for human progress. In fact, in most instances, truthiness is good enough. In fact, verisimilitude is not only good enough, it's darn helpful. Consider baseball. Newtonian mechanics describes the arc that the ball takes through the air pretty much to a T. The rise, the apex, the fall, the velocity up, the moment it hangs suspended, and the arc that it curves through the air as it launches from Chicago Cubs third baseman Chris Bryant's bat up and away into the White Sox bleachers. The story, however, is incomplete. A complete story, a true story, a complete model would have been able to tell you all possible outcomes. It would have been able to tell you what would have happened if Bryant had used enough muscle to knock that ball near to the speed of light. Yet if he had, a model that only relied on Newtonian mechanics would have been completely wrong as to where and when that ball would have landed, if ever. And if that ball had been the size of a quark, a model that ignored quantum theory would have not been able to tell you its spin or position, or much less tell you why only one of those measurements would have been possible. The state of today's science is that there is no one story that could have covered all possible descriptions. We aren't there yet. Physics and physicists are still working on that. Cartwright would probably say good on you to those searchers after that truth, and in the meantime would have been handing out maps to baffled White Sox outfielders to show them where to begin looking for that missing ball. Because while wrong, Newtonian math still works pretty well. And science is exactly like that. Even when all of the data has not been added to the model, even when the assumptions are not all accounted for, even when the laws of nature are missing or incomplete, the predictions are pretty amazing and a darn sight better than a guess or just wishful thinking. Even though the good and proven and reliable theories are not actually true, the predictions are wicked accurate. And that is why, even when the consensus is still out, even when there is no unanimity among practitioners, even when there are holes, gaps in the knowledge and understanding, even then, science is still more useful than partisanship. In curbing the effects of climate change, going it alone doesn't work, but international collaborative plans do. In curbing the spread of wildfires, raking doesn't work, but managed burns do. In curbing the spread of a disease, wishing it away doesn't work, but masks do. All three of these, collaboration, fire management, mask efficacy, all three of these did not pop out of nowhere. All three are the result of, in some cases, decades of scientific argument, experiment, and debate. We can ask if these explanations are complete. Totally, we can totally ask that. But if answering that question means doing nothing until the answer is known, until the science is settled, until the debate is over, until we have the truth, we have forgotten the point. The model was not the goal. Science itself was not the goal. Science is only a tool, a human tool. As imperfect as we are, as amazing as we are. The fact is, we know more now. The challenge, the point, is to use what we know now to do better now. In our search for truth and meaning, may we never let perfection become the enemy of the good. May we never forget that the model is not the point. May we remember that science is only a tool, and may we never cease our journey to always aim at truth as we continue to grow toward greater compassion, greater connection, greater understanding, and work to create a world where we all can live, all can thrive, and all can flourish, both the weird and the wonderful. May it always be so. Amen.